Welcome to this second lecture about electricity production. It is again about turbines, but this time turbines without any combustion part. These turbines use renewable sources from the earth core, wind or water. And contrary to what is indicated in the table, we take geothermal steam turbines into account. We even start with them. The core of the system is the generator, producing alternative current based on Faraday's law. This was the subject of another lecture. And just like in gas and steam turbines technology, the rotor is rotated by a turbine. But this time, there is no combustion of fuels to create gas or steam to action the turbine. The steam comes directly from the ground. You may remember that the temperature deep in the earth differs a lot depending on the location. In some places, steam at more than 200 degrees Celsius can be obtained, which is very convenient to power a turbine, like on the picture. So, instead of using the steam for heating application, it is this time used to produce electricity. Sometimes it is not steam that is pumped from the earth, but brine water under high pressure, which is first flashed, depressurized then to steam when coming out of the ground. However, there are many other locations in the world where the ground temperature is much lower than this 200 degrees, making it impossible to make steam with a pressure high enough to drive the turbine. This problem is solved by using closed cycles using a refrigerant with a boiling temperature lower than the one of water. These refrigerants can evaporate at low temperature, and we call this an organic Rankine cycle, ORC. Maybe you remember another lecture in which we saw that freons, ammonia or propane can evaporate at very low ambient temperatures. The groundwater circulates now through a heat exchanger, giving its heat to the refrigerant which evaporates, and this is the vapor that drives the turbine. From the refrigerant point of view, the turbine acts as the expansion valve in a heat pump cycle. The refrigerant vapor is brought back to a low pressure and low temperature. At the exhaust of the turbine, the liquid refrigerant is pumped into the heat exchanger where it evaporates. When ammonia is used, the temperature at the exhaust of the turbine is still much too high for the ammonia to condensate, but this is solved by having the ammonia absorbed by water. The water-ammonia mixture is then heated in the heat exchanger, by which ammonia vapor is created again. This is the so-called Kalina cycle. And of course, from policy point of view, the primary energy and the CO2 equivalent emissions are zero. In practice, it is not the case, as we need pumps for the geothermal wells and for the steam and refrigerant circulating in the turbine. A part of the electricity generated by the plant can be used for this, of course. There is, however, a kind of competition between using geothermal heat for heating applications or for electricity generation. Here too, just like in the other turbines, it is very well possible to produce at the same time electricity and heat. See here that heat at 70 degrees is used for district heating. So combined heat and power, CHP, is possible here too. Let's now climb up towards Earth's surface and look at how electricity can be made with the power of water, hydropower. This is also turbine technology, and here too there is a generator producing alternative current powered by a turbine. But this time the turbine is powered by water flowing from a higher to a lower elevation. This can be done by using a simple run-of-the-river system which will produce electricity only when the flow rate of the river is large enough. This is applied in small local systems. It can also be done by storing water in a dam or reservoir in such a way that a continuous flow of water can be ensured. Those are the large hydropower plants with powers up to 20 gigawatt for the largest ones. The maximum power that can be extracted is the potential energy of the water flow rate falling from height h1 to height h2, and is therefore mass flow rate times gravitational acceleration, which is 9.81 square meter per second, times height difference. As for the losses, there are only the mechanical losses in the turbine and the generator, so the efficiency is high, around 95% for large plants and 80 to 85% for smaller ones. However, as the energy source is fully renewable, the efficiency can be considered to be infinite, and the primary energy and related CO2 emissions are zero. Cogeneration of heat and power is not possible, as there are no heat losses, only the very small ones relating to the losses in mechanical efficiency. On the left, a picture of the Akosombo hydropower station in Ghana on the Volta River with a power of 1 gigawatt. In the middle, the Three Gorges Dam on the Yangtze River in central China, delivering 22 gigawatt. And on the right, a typical turbine for hydropower. You see that the shape is different from the ones of steam and gas turbines. Although hydropower can be said to be sustainable in the sense that it is carbon-free, do not use any fossil fuels and can protect from flooding downstream, there are important limitations to its sustainability in the broader sense, especially when it comes to large plants with huge reservoirs. To construct such large dams, tens of square kilometers land are flooded, destroying villages and cultural and natural heritage, and forcing thousands or even millions of people to move, so careful considerations are needed. Finally, hydropower can also be used as storage for excess electricity generated by the sun, photovoltaic panels, or by wind. When their production is very high and exceeds the demand, the electricity can be used to pump water into a reservoir. This reservoir will produce later electricity by hydropower. This allows for a good integration of diverse forms of intermittent renewable energy. Next to the classical hydropower, tidal energy from oceans can be used as well. Tidal hydropower is a constant source of power on Earth, as tides are induced by the rotation of the moon around Earth, and there are 2 times a day ebb and flood, inducing water flows and height differences. Some tidal turbines make use of the induced water flows, that is the kinetic energy of the flow, other from the water height difference between ebb and flood, therefore the potential energy of water, by storing water in reservoirs at high tides. These ones work like classic river hydropower at ebbing tide. Additional reservoirs can also be used to produce electricity between the tides. Such tidal power plants can be found, for instance, in the Netherlands, see picture above, South Korea on the Shiva Lake, see picture below, or France in Saint-Malo, where the height difference between ebb and flood is more than 10 meters, delivering a power of 24 megawatt and more than 500 gigawatt hour annually. There are also developments in the field of wave power, in which waves' kinetic energy underwater is converted to electricity by underwater floating turbines, like kite turbines. However, the potential seems to be much lower than the one of tidal energy. After the energy from the Earth core and from water, it is time now to go to higher spheres and to look at how to produce electricity from wind energy. Here too again, AC electricity is produced in a generator, which is driven by a turbine. The generator is placed in the box behind the blades, the nacelle, together with a gearbox in order to increase the rotation velocity of the generator coil. The electricity produced goes through electrical wiring along the shaft to the grid. The maximum energy that can be converted from wind coming perpendicular to the turbine at velocity v is its kinetic energy, which is half its mass flow rate times the square of the velocity. As the mass flow rate is also equal to the volume flow rate times the specific mass of air, and the volume flow rate is the surface area corresponding to the diameter of the turbine times the velocity, we end up with the formula above left. However, this formula is only right if the wind velocity on the back of the turbine is 0, which is never the case, and it can be shown that for the type of turbine on the slide, the formula must be multiplied by the bed's efficiency, which has a maximum of 16 divided by 27, which is 0.59. Other types of turbines may have a bit higher Betz factor. The maximum power Pmax is therefore defined as the wind power times Betz efficiency. In practice, approximately 45% of the energy contained in wind can be transmitted to the rotor, that is P rotor. And then there are the mechanical losses in the gearbox, around 5%, and around 10% losses in the generator, which brings us to an average electrical efficiency of 23%. But that's low, but not really a problem, as wind is fully renewable. Its primary energy use is zero, as are its CO2 equivalent emissions. There are a lot of losses in such a wind turbine, but they cannot be recovered. Gone with the wind. So, combined heat and power is not possible. Be also aware that the larger the height of a turbine, the higher the wind velocity and the more power it can produce. A wind turbine is designed to achieve a maximum power from a certain wind velocity. Below this velocity, the turbine will work in partial load. Above a certain velocity, 20 meters per second in the figure, the turbine would be stopped. Producers of wind turbines give in their specifications the rated electrical power, which is nothing else than the nominal power at the maximum wind velocity the turbine can bear. They also give a power curve as function of the wind velocity. For a quick and rough estimation of the total annual electricity production, one can take the average annual wind velocity at the location and multiply the corresponding power by the number of hours in a year, which is 8,760. For instance, in the Netherlands, the average velocity at the height of 100 meters is around 8 meters per second, meaning that a turbine of this height would produce annually 20% of its rated power times 8,760, which is 1,752 times the rated power. 752 is the number of equivalent full load hours. If we take a turbine of 7 megawatt, we come to a production of 2,264 megawatt-hour annually. In fact, such a large modern turbine would achieve easily double this electricity production. Most large turbines will have a steeper power curve. This is why it is essential to use a specific power curve corresponding to the turbine under consideration. Wind turbines can be found in many power ranges from a few kilowatt up to 12 megawatt. 12 megawatt is the largest turbine in the world from GE. You should imagine it is 260 meters high and the turbine itself has a radius, the length of the blade, of 107 meters. Such sizes are only possible for offshore turbines, as you see in the picture left below. Above left, an onshore large wind park in California, and in the middle above, a so-called Darius turbine. It is a turbine with a vertical axis for smaller powers. In general, small turbines have a limited efficiency, the Betz factor is low, and the electricity production may be a bit disappointing. And the two last pictures show very interesting examples of integration of turbines into buildings. In this lecture, we reviewed 3 turbine technologies aimed at producing electricity. Opposite to the conventional turbines based on fuel combustion, these ones are based on other principles. However, they are all equipped with a generator and produce alternative current. The first technology uses geothermal heat to produce steam to drive the turbine and therefore the generator. Depending on the temperature of the geothermal heat, different cycles can be applied. The second one is based on hydropower, a very efficient way to convert potential and kinetic energy of water into electricity. Tidal energy is part of hydropower. The third one is wind power, a powerful technology at places with a lot of wind. For these 3 technologies, basic data and formulas were given to make simple calculations of power and electricity yield. Primary energy and CO2 emissions can be considered zero anyways. Thank you for your attention.